So, seasonality, the intra-annual variation in light, temperature, and precipitation is especially important on a human scale because it determines the timing and the length of the annual growing season or seasons, which in turn govern the availability of food. Now, it's therefore something that would be very useful for us to know about when trying to reconstruct ancient and prehistoric productivity, both during but also between these periods of rapid climate change. But traditional climate proxies in the Aegean and the East Mediterranean in general are hard-pressed to provide decadal resolution, much less seasonal. So when Jan and Simon invited me to participate in this workshop, I decided to take the opportunity to see if there were other archives that were available that could be combined with traditional climate proxy data that might give us a better idea of what the seasons of the year were like in late Bronze Age Crete. Now, the seasons of the year have inspired music, art, dance. Oh, let me turn that up a little bit. For thousands of years. Dance, dance of the hours, black vases showing the hore, reliefs showing the hore as well. But for most of us in this room, I think we think in terms of 4 seasons: spring, summer, fall, and winter. But this isn't true for all latitudes or cultures. Certainly in temperate and subpolar regions, 4 seasons are the norm. But in hot regions like the Mediterranean, maybe 2 or 3 seasons are recognized: a rainy season or a wet monsoon season and a dry season, and sometimes a cool or mild season. Other cultures think in terms of seasons associated with events such as the hurricane season, the tornado season. I live in Tornado Alley in Texas. It's very exciting. Or, as in ancient Egypt, the inundation season, when the Nile flooded its banks, the emergent season, when the waters retreated and you could plant, and the harvest season, when crops were harvested. So how many and what kind of seasons might have existed in late Bronze Age Crete? Let's see what we can find out. So first, let's just review the proxy data that we've been hearing about yesterday for the South Aegean and see what we can come up with. Now, most of you today, as well as others, show that in the second half of the first millennium BC, temperatures began to drop. And by the end of the Bronze Age, shall we say 1177, sea surface temperatures in the South Aegean had dropped to about 2 degrees centigrade. Now, this is clearly seen in the core taken by Elko and processed by him and his colleagues, and which he discussed yesterday. And he further notes that such a cooling of the top 200 meters of the sea would require a significant atmospheric forcing and should have had sharper and more pronounced effects on land. He proposes as a mechanism severe northerly winter and early spring weather linked to the Siberian high, which I call the Siberian Express. And as you can see, highlighted in blue, that the temperatures dropped, highlighted by the orange arrow, just above the Santorini ash deposit, which can serve as an unimpeachable relative chronological reference point because we're still debating exactly when the eruption took place, and after a short gap in the record. By the time the record picks up again, we're in the later late Bronze Age, maybe about 1300, plus or minus a century given the chronological resolution of the core, suggesting that colder temperatures began shortly after the eruption, maybe in the 1500s, maybe in the 1400s BC. Now, a new speleothem from Kocain Cave in southwest Turkey, taken at about 870 meters and studied by Ozan Göktürk for his doctorate. I don't know if I pronounced his name correctly.
Kocain is the
Co-
Kocain.
Oh, Kocain. Okay. I think cocaine is much more interesting. Okay. Anyway, it preserves a detailed record of winter temperatures for this period based on carbon-13 isotope analysis. And this indicates a cold spell for about 70 years from 1620 to 1550 BC, which is rather intriguing, of course, when we think about at least what some of the people date this core to. Date the Minoan eruption of Santorini to. Then, winter temperatures become very warm, or temperatures in general become very warm, until about 1000 BC when they drop significantly. So the thing is that this doesn't, the chronology of this cold period and the chronology of the cold period from the marine cores are different. So is it because of the dating resolution of the two archives? I don't think so, because even though the resolutions are different, I think that the cold temperature, that it's not enough to make up for the difference in time between 1400 in the Aegean Sea and 1000 in this particular cave, Speleothem. So I wonder if the Siberian Express didn't actually, when did it start really impacting this part of Anatolia down here in the south area above Antalya? So what about the precipitation regime, though, for the late Bronze Age? Does the aridity discussed in so many of the proxies from Anatolia show up in Crete at this time? Well, the core from Kournas and Limnis that Mark presented to us yesterday suggest no. They suggest that we had mainly wetter conditions, but of course that's key on whether these isotopes that we measured are actually measuring evaporation, as we discussed yesterday. But we have another archive, which is the Pollen archive from Crete, from the site of Delphinos here on the coast, which also shows that moisture-loving trees were increasing, tilia and elm. Here we go, over here. I know it's rather long, but up at the top you can see these two trees just coming in around the Santorini ash layer. So instead of sticking to any kind of a relative chronology in this core, they're not, tightly dated, but if we stick up there where the ash is, I think we're pretty safe with the chronology for being in the late Bronze Age. So these trees are increasing, but they start increasing before the Minoan eruption of Santorini, when, according to the LC21 core, winters were quite warm. But they persist after the eruption in this diagram, even tilia. And tilia doesn't grow in Crete today. It's too arid. But it's a drought-intolerant tree, and it doesn't tolerate particularly summer drought. So I think it's interesting that we still have it at this time in the late Bronze Age, along with olive pollen. So here's the olive profile. And you can see that the two peaks in the olive profile date back to the Neolithic and the early Bronze Age, and they're closely paralleled at other cores at Tersana out on the Akrotiri. But it begins to recover up there around the eruption period, around the tephra deposit. Now, when the pollen record picks up again in this area at Kournas, which is just down to the southwest, just a few kilometers away. And Mark discussed yesterday some of the dating problems with this core. So we have a radiocarbon date at the bottom of the core before the pollen record actually begins. So once you get into the pollen record, my guess is that it's probably in the early Iron Age at some point, and we have olive declining from a peak that is very similar to peaks and declines that we see on mainland pollen cores, which are, some of them are better dated, and this dates to the Archaic, Classical, and Hellenistic period on mainland Greece. But there's no tilia. this is actually in an environment today which would be much more suitable to Tilia to survive in this area. But it's not here, and it never shows up in the pollen records of Crete again. So this suggests much drier conditions coming in at some time between the end of the Late Bronze Age and the Early Iron Age. Now, to sum up, the climate proxy data, such as it is, indicates colder winters and springs on Crete, accompanied somewhat later by increased aridity. Now, an important consideration is how this cold weather and eventual aridity would interact with the topography of Crete. Now, one of the things that Elko noted again was that during these periods when these winter outbreaks occurred, we should expect intensified winter frosts along the northern and northeastern sectors of the Aegean coast, so up by the Dardanelles and Thrace, and milder frosts and snowfalls in the south after it had the chance to pick up moisture as it traversed some 600 kilometers down through the Aegean Sea. So once it gets that far, what is this moisture-laden air going to eventually slam into? Crete. You can't avoid it. There's simply no way this island can be missed. And now, I mean, mind you, the air sailed across a lot of other little islands, but they don't have enough relief to cause the air to drop its moisture load. However, Crete has these amazing mountains. The mountains of Crete rise over 2,000 meters within 20 kilometers of the sea. It forms this east-west barrier, and they would have forced the moisture-laden air up, causing it to cool, drop its load as snow and rain. And while Elko experienced his frigid time in 2001, something similar happened in Crete in 2004, and this is my house at about 100 meters elevation, buried under 2 feet of snow. So this is, I mean, in all my years in Crete, this is the only time I've ever experienced this. So it was quite an event. And today in Crete, the major freeze line is between 600 and 800 meters, depending on where you are. And for this reason, on the north slopes, olives are mainly cultivated below 600 meters, so some are as high as 800. And I've even found wild olive in a bitten down state as high as 1,000 meters in Crete, but I think it may well be a relic of warmer times when winters were warmer. On the south slopes of the White Mountains, I actually know of a cultivated olive growing at about 950 meters, so demonstrating the effect of the rain shadow and heat effect on the south slope versus the north slopes of Crete, which I think is interesting. So now, if one accepts the standard lapse rate of 1 degree C for about 100 meters of elevation, this would suggest at a minimum that the freeze line on Crete in the late Bronze Age cold period dropped about 200 meters. Now this is significant. This is a significant loss in cultivable land, at least cultivable in terms of the crops that we're familiar with for the late Minoan period. I mean, you could grow different crops, but we don't have any evidence for that. Today, these weather systems mostly occur in winter and spring, suggesting that during the late Bronze Age, early Iron Age cold spell, freezes as low as 400 meters, which would be about here, could have characterized the spring on the north side of the island, shortening considerably the growing season at these elevations. Low elevation aridity, which happened sometime after the Siberian Express began to frequent Crete, would have shortened the growing season on the coastal plains as well, squeezing the cultivable areas up into the foothills. Now, this means that the parts of Crete that would have been the least affected by these two phenomena would be the lower inland and the middle slopes of the island, roughly between about 100 meters, so about where my house was, and 400 meters elevation. Now, I wish I had a better illustration for this, but that would be on the north side of the island. And 400 meters is the white area along the north coast. And on the south coast, it would have been a bit lower, a bit higher, and would probably been about 600 meters, which takes you into that sort of lime green area on the south side. And I think I like to call this magical band of land, which I think is fairly stable as far as human cultivation and settlement goes on Crete, the Camelot zone. So it's easy to remember. So now my reconstruction of where this might be is a guesstimate, but it's one that can be tested with computer modeling for those who do that sort of thing. And for those who are interested in Bronze Age Crete, I think it would be a really worthwhile exercise. So maybe there are some PhD students out there that would be interested in modeling this kind of information. So now that we have at least some idea when and where the last frost might have been, in the late spring at about 400 meters elevation, but what about the first frost? Is there some way to get it when winter started? A possible approach is phenology, the study of periodic plant and animal life cycles and events and how they are influenced by seasonal and interannual variations in climate as well as habitat change. Now for plants, variables considered are bud burst, leaf unfolding, flowering, fruiting, and leaf fall. Numerous studies indicate that temperature and light are the prime drivers in the early stages of plant growth in the spring, especially temperature. And for this reason, the growing season requirements of a plant are measured in the number of growing degree days. Now, growing degree days are calculated by taking the average of the daily maximum and minimum temperatures minus a base temperature, which is usually about 10 degrees C, but it depends on the plant. Modern studies of phenological phenomena during our current period of climate change have found that many systems are already changing. A phenological examination of 542 plants in species in 21 European countries from 1971 to 2000 show that 78% of all leafing, flowering, and fruiting records have advanced, and only 3% were significantly delayed. This is called season creep. Now, if all systems adjusted simultaneous to climate change, animals and plants, there wouldn't be too much of a problem, but of course that doesn't happen. And instead what we have are increasing mismatches between the previously coordinated cycles of plants and animals, such as flowering occurs before pollinators become available, which has negative consequences on reproduction. Shorter and warmer winters don't allow some trees to cold harden, which results in frost damage when winters are more severe. Early buds and flowers are killed by what 10 years ago would have been considered a standard frost. Now, a study in Spain has noted that species a few decades ago that clearly showed different flowering periods are now overlapping and consequently have to share the same pollinators. So the impact, I think, of these mismatches is it's an amplifying effect that we would see when the temperatures change. So what about the late Bronze Age? Wouldn't similar phenological mismatches have occurred, especially with pronounced changes in winter temperature and snowfall? So how might season creep have impacted crops that were growing in late Minoan Crete? How frost tolerant were they? How drought tolerant? How long of a growing season did they need? Now, we know from macrobotanical and linear bead tablets that the main crops were barley, wheat, olives, grapes, figs, almonds, and a variety of pulses. So let's look at olives. Olives are not frost tolerant, but they do need a cold period down to about 10 degrees C in order for them to have a winter rest period. Minus 5 degrees C will severely damage the trees. But unless the tree is killed the ground freezes and the tree's killed, it'll probably resprout. So what we're really looking for permanent damage in the olive crop would be when the ground freezes. So they are water tolerant, drought tolerant, we know that, but even severe water stress, like in the late season when the fruit's setting, can cause a yield loss. And because the buds in olive are set the summer before, if the winters are really severe, it's going to damage the buds and they won't begin to burst and then leaf out and so forth as they should. Now, a study done by Osborne and his colleagues in 2000 found that olive flowering is a useful indicator of climate change because it is so closely tied to spring temperatures. And they found that olive flowering advanced by 8.5 days per 1 degree C. So if we're estimating 2 degrees C difference in temperature, we're looking at a difference of over 2 weeks in the flowering time of olive in Crete. Olive is also not snow tolerant. We know this from 2004 when we had our olive trees covered in snow and we had all this bough breakage. Now, of course, they eventually recovered, but it was a bit of a disaster for several years. It took them quite a while to recover. Now, what about vines? Now, grapes do best if the mean temperature for the coldest month is not less than 1 degree C, minus 1 degree C. Very low temperatures, again, will injure vines. Freeze injury due to dormant vines in the wintertime begins at about minus 15 degrees C. So, by looking at this phenological data, we actually are being able to get some kind of range in what the tolerable winter temperatures might have been. Now, grapes need a warm and dry spell before harvest. Rain in the harvest season damages the crop, which I'm very familiar with. I have grapes at my house in Crete, and if it rains in the fall before I get them collected, it's really a problem. So a number of studies have also used historic data on vine harvest to reconstruct summer and spring and summer temperatures for the Little Ice Age. And according to Meyer and his colleagues, or Meyer, I don't know if I pronounced it right, a later grape harvest of around 12 days corresponds to about 1 degree centigrade increase in April-August temperature. And they also found that large volcanic eruptions can lead to significantly later grape harvests, even 1 to 2 years after the event. Excuse me. Now, other crops, there we go. Other late Minoan crops would also be impacted by this if we look at their frost tolerance and drought tolerance and growing days. So barley is not frost tolerant, but it has a fairly short growing period, so I don't think maybe it would have been too much of a problem. Wheat is frost tolerant, but has a longer growing period, but I think, again, that wouldn't be too much of a problem. Lentils, again, would have survived okay, but they have a fairly long growing season. So I wonder if the shorter growing season in the spring might have affected them. It really depends on how hot the summers are. Almonds would have done okay, but they have a very long growing season. Flax probably would have been fine because it's both frost tolerant and drought tolerant moderately. Figs, interestingly, which were a very important ration in the Linear B text, I think would have done just fine. So phenological considerations suggest that shorter growing seasons and spring frost would have impacted all of the late Bronze Age crops, primarily by delaying leaf unfolding and flowering, and thus probably shortening the available growing season. I say probably because we don't know much about the conditions in summer or fall, although we can propose that at least part of the summer was still dry with warm to hot temperatures based on the requirements of figs and grapes for their fruit to come to maturity without damage. Now, in addition to the plants themselves, there is a rich source of phenological data in ancient weather lore. Like many cultures, the ancient Greeks had a rich tradition of phenological proverbs and sayings, which indicated time for some kind of an activity to take place, such as the migration of birds and the growth cycles of plants, which were used to predict when it would be time to plant, plow, and harvest when seas were safe for sailing. Now, Theophrastus, for example, he says, the thrice the mastic, that is Pistachio lentiscus, buds and thrice wax ripe its berries, and each crop in turn brings the sign for the sowing. Men divide the sowing into 3 seasons, early, middle, and late. So again, this would be something that would be very interesting to coordinate with the paleoclimate information from other kinds of archives that we have with the growing requirements of Pistachio lentiscus. Hesiod, in the 8th century BC, says, when one first sees on the topmost shoot of a fig tree leaves as large as the footprint of a crow, then the sea is passable and the spring season has arrived. So again, I think if we look at the phenology of the fig tree and relate it to the 8th century climatological information that we have from other archives, we may be able to get some kind of interesting matches. Homer even, taking us back to the early 8th century BC, tells us that the cranes flee the winter and the unspeakable storm and make for the streams of ocean. And we know that today they still go down into the Levant every winter. So this rich material, I think, can be mined for phenological relationships in the 8th century, coordinated with other kinds of climate proxy data, such as stable isotope records, and see how they compare to today, and then maybe use it as a baseline for the Bronze Age. Now, the Greeks also used astrometeorology to predict when it would be time to plant, paying special attention to the heliacal rising and settings of fixed stars, solstices, and equinoxes. For example, Hesiod notes, 50 days after the summer solstice, at the arrival of the end of the season of weary heat, that the time for mortals to sail, then are the winds orderly and the seas propitious. Now, there are lots and lots of these that I think, again, we could coordinate into some interesting phenological insights into the seasonality of the 8th century. A snag, of course, is that, a lot of these observations are not the same as they are today because of the precession of the equinoxes, but they're wonderful computer programs that can project when the stars rose and fell in the late Bronze Age in Crete at a particular geographical period. So here you can see that the spring equinox has moved from about 2000 in BC to 1000 BC, from the period where the Pleiades might have been associated with it, down going towards Aries. Now, determining which stars were observed, calculating what year they were observed, when in the year, and considering what they could have been a sign of might provide us some more information about seasons in late Bronze Age Crete. And the work of Mary Blomberg and Göran Heinrichsen suggests that Minoan buildings and peak sanctuaries were aligned to certain celestial events and fixed stars. Now, one of the most important ones is Arcturus. And Arcturus is the brightest star in Bootes and was repeated alignment for a number of peak sanctuaries. So from Minoan to Archaic times, the heliacal rising of Arcturus happened in mid-August. So why would this be of interest to the Minoans, especially at a peak sanctuary? Well, Hesiod tells us that in the 8th century, the heliacal rising of Arcturus marks the start of the grape harvest. But in his time, the star rose at the beginning of September, some 2 weeks later. So my question is, was the grape harvest that much earlier in the Minoan palatial period? Were conditions that much warmer that we would have been harvesting grapes in the middle of August? Maybe. Certainly some of the paleoclimate archives that we have suggest that conditions were particularly warm then. Or was it something else? I think these kinds of observations can lead somewhere eventually. Now, odds are the late Minoan Bronze Age, they did these kinds of observations, but we don't have any very much information about this. Little survives. Mycenaean buildings on Crete show different alignments to the Minoan ones, but there's not a lot there. There are not a number of enough samples. But what about weather lore? Certainly, Bronze Age cultures in Crete did not exist in a weather vacuum. Mesopotamia and Egypt contain a rich literature on weather lore. A good example is the Sumerian Farmer's Almanac, which would be contemporary with Middle Bronze Age Crete, just one of many examples. But what about the Linear B tablets? Are these texts, which date to the 13th century BC and largely come from Kournas in Crete and Pylos on the mainland, but which are extremely brief and frustrating, what do they say about weather or seasons? They mention a lot of other things, foodstuffs, rationing, personnel, religious events, and so forth, but they are pretty silent about weather and the timing of the seasons. There are no words for spring, summer, autumn, or winter. There is a word for month. And there were several names of months also in the Linear B record, so we know they were keeping a calendar, which makes it all the more likely that they also had the kind of seasonal folklore that we're interested in. At Kournas, there are at least 6 month names, but of course we don't know when they actually occurred in the year. At Pylos, there are 3, and one is Porowitoyo, which is in the month of sailing. Now, according to Hesiod, the sailing season occurred from March to October. So again, this is 8th century. And it seems likely that the month Porowitoyo occurred sometime within this 7th to 8th month period. And by looking at phenological relationships in the stored products, the products being collected and the activities being done, it seems that at the time the tablets were fired into immortality at Kournas, the sheep had not only been shorn, but their wool had been distributed to workers to be made into cloth, and the grain harvest was begun but not completed. This suggests that this month had to happen not at the beginning or the end of the sailing season, but in the middle. Odds are these relate to the ETISIAI winds, which blow today from the northeast and northwest from May to October and are especially strong between July and September. Now, I think there's more phenological information that we can get out of the Linear B text. I'm not a Linear B scholar, but I look forward to collaborating with Lisa Bendel, who is interested in calendrics and this sort of thing, and we're doing a project on this. So what can we conclude about the seasons in the Late Bronze Age? By looking at orographic considerations, phenology, ancient weather lore, and archaeology, we can tentatively maybe reconstruct the seasons as something like this in the Late Bronze Age. So springs were cool, becoming colder. Late frosts caused delayed bud burst, leaf unfolding and flowering, shortening the growing season. Snow would probably lie late on the high mountains, delaying the movement of flocks, perhaps causing overgrazing at lower elevations. In the summer, we know that there was a sailing season at the time of sheep shearing and the beginning of the grain harvest. We know that they were interested in wind. There's a cult of the wind, and that it was at least warm and dry, probably late in the second half of the summer, in order for the fruit of figs and olives and grapes to properly dry. The autumn is our big hole. I wish we could get at more of that, but maybe as we pursue these phenological studies, we'll be able to do something more there. Winters were periodically extremely cold, snowy, cultivation confined to the Camelot zone between 100 and 400 meters on the north and 100 and 600 on the south. So it's a start. There we go.